Hi, I'm Wei Xingzhang. In this talk, I will present a new modular programming style called compositional programming. An important aspect of programming is how to model data structures and operations over those data structures. In object-oriented programming, data structures are modeled as class hierarchies. Operations on the data structure are methods implemented throughout the class hierarchy. In functional programming, data structures are modeled as algebraic data types. Operations on data structures are defined as functions that perform pattern matching on the algebraic data type. Unfortunately, conventional OOP and FP suffer from the expression problem. It is easy to add new variants in object-oriented programming by defining new classes, such as a class for multiplication. However, it is hard to add new operations modularly, as it requires modification on the whole class hierarchy. In contrast, it's easy to add new operations in functional programming such as printing, but it is hard to add a new variant. We have to modify the data type definition with the new constructor as well as all existing functions. Note that the printing operation depends on the evaluation. To express such dependencies modularly poses new challenges to modularity. Existing design patterns can only partly address these problems due to a lack of proper mechanisms for modular dependencies and compositions. These design patterns often result in heavily parameterized and boilerplate code. We propose a new statically typed modular programming style called compositional programming, which not only solves the expression problem but also deals with modular programs with complex dependencies. We present a language design for compositional programming called CP, whose semantics is given by elaboration to FI+, a recent calculus that supports disjoint intersection types, disjoint polymorphism, and nested composition. We prove that the elaboration is type-safe and coherent. We show how to model attribute grammars in CP without explicit definitions of composition operators. We present a novel technique called polymorphic contexts that allow modular contexts in modular components. And we implemented the language in Haskell. We conducted several case studies to illustrate the usability of the language. We introduced CP by solving the expression problem first. The arithmetic language is described by the compositional interface (ASPIC), which declares two virtual constructors lit and add. The expression data type is captured by a sort surrounded by angle brackets. Sorts differ from type parameters in that they are used to capture the return type of virtual constructors and allow dependencies to be modularly expressed. Operations are defined as traits that implement the compositional interface. The trait eval_num implements ASPIC by instantiating the sort asp as eval. Traits in CP are first-class citizens. In the body of eval_num, each virtual constructor defines the eval method using the method pattern syntax, which is syntactic sugar for defining nested traits. The outer trait, eval_num, is called a trait family because it contains nested traits. The printing operation is defined in a way similar to evaluation by instantiating the sort as print. The generic trait add defines a modular term independent of any operation. Traits in CP can have a self-type annotation, which provides a modular way of injecting dependencies on other operations or constructors. By annotating self as explicit, the lit and add constructors are in the scope of the body. Then we can use the new expression to construct a test object of 4 plus 8. At the heart of compositional programming is a powerful composition mechanism called nested composition. Nested composition allows the composition of multiple trait families. This mechanism can be viewed as a form of multiple trait inheritance, but with the added ability to recursively compose nested traits automatically. The nested composition is performed by the double comma merge operator. The type application supplies an intersection type of eval and print to add. Since the self-type annotation has been instantiated as eval and print, to meet such requirement, the trait has to be merged with some trait that simultaneously implements eval and print. This is done by merging it with eval_num and print_num. After nested composition, we get a trait that implements both evaluation, printing, and a test object. Now, tests can be either printed or evaluated. The result is 4 plus 8 is 12. Variants can also be modularly added in CP. Adding multiplication is done by extending ASPIC with an actual virtual constructor mul. eval_mul and print_mul implements the extended compositional interface mul_sig by complementing a definition for mul and inheriting the corresponding trait family defined for x plus 6. We can now define an extended term that uses multiplication. As shown by xmul, methods defined by parents can be overridden. The overridden method can access the parent's method via a supercall. In this case, we override the test object by multiplying the test object from x by add by 4. Then we instantiate the extended trait families into an object, E prime. E prime's test object can be printed and evaluated as 4 plus A times 4 is 48. Besides expression problem, CP can model programs with complex dependencies modularly. We use examples from S-attribute grammar to illustrate different kinds of dependencies. The first kind of dependency is child dependencies, where an attribute depends on other synthesized attributes of the children. The example is an print operation that depends on evaluation shown before. The dependency is expressed by instantiating the sort as eval and print, denoting that the trait implements both evaluation and print. By inheriting eval num, only printing needs to be defined. Although the code from eval num is reused, it tightly couples printing with a particular implementation of evaluation, making it less modular. The dependency can be weakened by changing the ampersand in symbol to percentage symbol and removing the inherit clause. This is a special way of expressing dependencies on sorts. Now, print child cannot be instantiated alone. It should be merged with some implementation of evaluation like eval num or any other implementation with the same type as eval num. A second form of dependencies is self-dependencies, where an attribute depends on other synthesized attributes of the self-reference. This example prints out an addition to 0 when it self-evaluates to 0. This is done by adding a self-annotation to the method pattern. The third form of dependency is mutual dependencies, where attributes are interdefined. In this case, print mutual and print args cause each other to omit outermost parentheses when printing. The dependency expressed again using the percentage symbol. A frequently occurred problem is that different modular components may require different contexts. Initially, evaluation on literals and additions requires no context. When data expressions and variables are introduced, we need a map from variable names to its value. The signature of eval has to be changed for taking an additional parameter. Eval num has also to be modified so that eval num and eval var can be composed. What if another context is needed? For example, a new context is introduced for evaluating let bindings for functions. Again, we have to insert another parameter to the evaluation signature and change all existing evaluation components. Such a way of adding contexts is highly non-modular. Existing code has to be modified when a new context is needed, and the contexts are exposed to components that do not actually use it, making it possible to accidentally change the context. We introduce a novel technique called polymorphic contexts that allow modular and encapsulated contexts. The signature of eval needs to be changed to a function from the type parameter context to int. When defining eval num, the context parameter is kept abstract. Now, looking up a variable name will be rejected by the type system. When a particular context is needed, we intersect that concrete context type with the abstract context parameter when instantiating the sort. When declaring the type parameter context, it must also come with a disjoint constraint for that concrete context, meaning that context shouldn't be instantiated as a subtype of context n. This way, incoherence is ensured. This definition uses disjoint polymorphism, which is a special form of parametric polymorphism. Similarly, eval func is defined by constraining the context to be disjoint with context f and instantiating the context parameter as an intersection of context f and context. Now we show how to compose these components with different contexts modularly. We can define a polymorphic expression that uses all the constructs from the three components. We annotate self as an intersection of three compositional interfaces. We construct a test expression that applies a square function f to x, where x is bound to 9. Now we merge these components. For each evaluation component, we first do a type application that supplies an intersection of context types used by other components. We then merge them and finally instantiate it using new. We can now call evaluation on the test object by supplying an initial value for the two contexts. The result is 81. This slide shows the formal syntax of CP. A CP program consists of a sequence of declarations and ends with an expression. The semantics of CP is given by elaboration to Fi+, which is essentially a subset of the CP language. During the elaboration, declarations, sorts, and trait-related constructs will be eliminated. The elaboration builds on ideas from generalized object attributes and the denotational model of inheritance. A sort is elaborated into two type parameters for capturing negative and positive occurrences. The return type of a virtual constructor is lifted into a trait type. An extended compositional interface is elaborated into an intersection type. The type specified in the extends clause is expanded and intersected with the transformed right-hand side. Trait expressions are firstly desugared. The body is wrapped inside an open expression. Method patterns are desugared to functions that return single-field traits, and trait expressions are elaborated to functions that take self as arguments. When a sort is instantiated with dependencies, the two type parameters represent that sort are instantiated differently. In the case of print child, the sort is instantiated as eval %print. Then the first type parameter is instantiated as eval in print, and the second parameter is instantiated as print. This way, we can call both eval and print for the sub-expressions. A trait with inherits clause is elaborated into a merge of super and its body. Overriding is achieved by inserting a type annotation to super. The type annotation is computed by excluded the overridden methods from the type of the super. This graph gives an overview of the formal elaboration. There are several steps performed during the elaboration. The program is first desugared. The type checking relies on several relations. The type expansion eliminates all type declarations. The sort transformation transforms the right-hand side of a type declaration. Type translation eliminates trait types into function types. During type checking, the subtyping is checked, which relies on top-like types. Top-like types are types isomorphic to top. Also, disjointness is checked during type checking, which further relies on an axiom. We proved that the elaboration from CP to Fi Plus is type-safe and coherent. To further demonstrate the usability of compositional programming, we conducted 3 case studies. The first is a DSL for parallel prefix circuits. This case study examines the ability to solve the expression problem as well as the ability to declare simple modular dependencies. The language initially has 5 constructs and later extended with various operations and a variant extension. We compare our implementation with existing implementations written in Haskell, Scala, and Fi+. Our implementation is the most compact and modular. The second case study is a mini interpreter for an expression language. This language includes various features and they are defined separately and can be arbitrarily combined to form a product line of interpreters. This case study further examines non-trivial dependencies and how to model multi-sorted languages. The final case study is the C0 compiler, which is an educational one-pass compiler that compiles a subset of C into Java bytecode. The original C0 compiler is written in Java, and the semantics is hard-encoded in the parser, therefore it is non-modular. Randall et al. Modularized C0 using generalized object attributes in Scala. We compare our implementation with these 2 implementations. The Java version is the most compact because it is monolithic and non-modular. Compared to the Scala version, CP is much shorter. The reason is that more than 600 lines of Scala code is used for combinators and composition, whereas CP has native support for composition. As CP is just a prototype implementation for compositional programming, there's a lot of room for improvement. For example, we would like to add support for recursive types and type constructor to add expressiveness to the language. It's also interesting to investigate how multiple states interact with CP. Currently, type inference support in CP is quite limited. To summarize, we have presented key concepts of compositional programming and the language design called CP. Compositional programming combines ideas from functional programming and object-oriented programming and offers an alternative style to both. With compositional programming, programs with non-trivial dependencies can be modularized, and the applicability is demonstrated by various examples and case studies. Thanks for your attention.